Good morning, lads and ladies. Welcome back to Calc 2. Today is our last meeting before your second test. So I want to make sure that we do as much as we can to help prepare you guys today. Today is your day. I'm happy to solve whatever sort of problems you guys want to solve, talk about whatever sort of shit you want to talk about. I think it would be wise to remind you some of the material that's going to be on the test that is slightly older, right? So like improper integrals, stuff like that is on this test. Sequences are on this test. And of course, all of the series convergence stuff that we've done is on this test. So here's what I'm going to do. I am out of coffee and water, so I'm going to go refresh those. And while I do that, I would like you to type into the chat whatever it is you want to say today. It can be a problem number, it can be a problem type, it can be definition, whatever. I'm just nervous about this thing. So let me know what you guys want to talk about today in preparation for your exam, which remember is Wednesday, next time we meet. And we'll do that. Okay, I'll be right back. So pleasant. Enjoying that. All right. Here we go. So I'm going to flip over to the dot cam, turn on the screen share. We'll take a look at the chat. Looks like I just have one thing so far. Well, please let me know what you guys want to be doing. That's the best way to prepare you guys. So look at what you want to look at. So this, as always, is MAC 2312. Section number 004, which is Calc 2. Today is the 1st of November, 2021. I hope everybody had a safe and fun Halloween. Enjoying the nice cool weather we have here in Gainesville. It's a rare thing, it's quite lovely. Today we are reviewing for exam 2. And we can do whatever it is you guys want to do. So again, please let me know in chat what you want to do. I see Frank's requested number 24 from the most recent homework, so I will start there. But please let me know what you guys want to see. That's about to sign me up. Okay. So here's number 24. And we're looking at n factorial over n to the n. This is a bitch and a half. So good choice, Frank. Let's see what we can do with this. Let's see what we can do now. This is coming from the ratio test homework. It's section 11.6. So there's a strong hint that we should use the ratio test, even if they hadn't told us that explicitly. That strong hint is the factorial. Remember, factorials, ratio test. So this is out of the way. Oh, sorry. let's do it. We want to investigate the series n factorial over n to the n. Yeah, factorial upstairs. Summing from 1. Pretty much everything about this series is kind of tough to work with. The first question you might ask is, does this get through the test for divergence? Yeah, we can look at stuff from the study guide. I don't care. So do the terms of the series here, does an go to 0? Can anybody tell me that? Solution color here. Remember what the test for divergence says. It says if the limit as n goes to infinity of the an is not 0, then the series must diverge. So here we're looking at the limit as n goes to infinity of n factorial over n to the n. And again, remember, this is not the same thing as this. They're totally different animals. This is just a limit we can calculate that sometimes tells us about the series. This limit on its own is kind of tricky. I'll say that at the start. But I have shown you something in this class that trivializes this limit. It's a one-line solution. Can anybody tell me whether this limit is or is not 0? It is 0. Yep, that's correct. So Richard and Frank are both correct. This is 0. Not just bigger though. So Richard's comment, bigger or 0 because n to the n is bigger. Well, 5 is bigger than 3, but 3 over 5 is not 0, right? It's 0 by growth rates. Remember that n factorial is less than n to the n. This is like the far right-hand side of our growth rates theorem. So if you remember this, then you can tell me this, right? You can tell me that n factorial over n to the n goes to 0 by growth rates. What do we learn from this? If the limit of the ANs is 0, then what is true about the series? We have some disagreement in chat. Oh, we've got every flavor of disagreement that could show up in chat. So either we learn nothing, or we learn that the series diverges, or we learn that the series converges. I'm tempted to take a poll. Let's do it. So choice 1, series converges. Choice 2, series diverges. Choice 3, we learn nothing. All right, tell me what you think. If the limit of the ANs is equal to 0, what do we learn about the series sigma AN? All right, we got everybody in now. Good news is that the correct answer got the most votes. The bad news is that the two incorrect answers also got a lot of votes. We learned nothing, right? Remember what the test for divergence says. It says if the limit of the ANs is not 0, then the series must diverge. If the limit of the ANs is 0, the test is inconclusive. The way it's stated in the book is if lim n to infinity an is not 0, then the series S equals sigma an must diverge. And we like to remind ourselves that if the limit of the an is 0, the test is inconclusive. Right? And I promise you, some variation on this shows up in every single one of these tests. So in your exam on Wednesday, there will be some variation on this. Like if the limit of an is equal to 0, then the series converges, true or false? The answer there would be false. Right? If the limit of the ANs is 0, we don't learn a goddamn thing. There are plenty of series that converge and have the limit of the AN equal to 0. There are plenty of series that diverge and have the limit of the AN equal to 0. The only thing we can say for sure is if the ANs don't go to 0, then the series must diverge. So since the limit of the ANs here is equal to 0, TFD is inconclusive. All right. So yeah, this does squeak by TFD. TFD doesn't help us here. And you could burn a lot of time calculating this limit. It's not an easy limit to calculate if you don't remember this growth rate stuff. It's possible you use the squeeze theorem, but it's a lot of work because you got to work with the factorial, which is weird. You got to work with n to the n, which is weird. So I strongly recommend that you recall this fact. Okay, so the suggestion was to use the ratio test. And because we have a factorial, that is definitely the thing to do. Unfortunately, the ratio test limit here turns out to be somewhat tricky also. When using the ratio test, we calculate the limit as n goes to infinity, an plus 1 divided by an, which for this series looks like lim n to infinity. An plus 1 is, I'll put a big fraction here. An plus 1 is n plus 1 factorial divided by n plus 1 to the n plus 1. That's what we get if I swap all the n's for n plus 1s in an. And downstairs, I would have n factorial divided by n to the n. And all of this is in absolute values. And yeah, it looks scary, right? So the thing to do is to flip and multiply. This is, I'm going to ditch the absolute values. Everything here is positive. Make sure you write them in your first step. But if you're certain that everything is positive, you can get rid of them in the next one. I'll have n plus 1 factorial divided by n plus 1 raised to the n plus 1. And then I'm multiplying that by n to the n over n factorial. It's tricky. I'm going to work with the factorials first. N plus 1 factorial is n plus 1 times n minus 1 times n minus 2, all the way down to 3 times 2 times 1. And then I still have an n to the n upstairs. Downstairs, I have n plus 1 to the n plus 1. I'll leave that alone for now. And then I have n factorial, which is n times n minus 1 times n minus 2, all the way down to 3 times 2 times 1. Here we go. So here's n plus 1 factorial. And here's n factorial written out. That's all I've done in this step. I left n plus 1 to the n plus 1 alone, and I left n to the n alone. And I'm going to cancel the n factorial with the copy of n factorial hiding inside of n plus 1 factorial. So this n with this n minus 1 with this n minus 1, n minus 2, all the way down to 3 times 2 times 2. And what's left is the limit as n goes to infinity of n plus 1 times n to the n divided by, now n plus 1 raised to the n plus 1. If I had dog shit raised to the n plus 1, that would be dog shit to the n times dog shit to the 1. Well, it's n plus 1 being raised to the n plus 1. So that's n plus 1 to the 1 times n plus 1 to the n. Just rules for exponents, right? Could ask a college algebra student to write that. And you see that the n plus 1s go. Boom, boom. And we're left with the limit as n goes to infinity of n to the n over n plus 1 to the n. And this is what I meant when I said the ratio test limit is tricky. Not the stuff we've already done, that stuff is trivial. But just this. This is a weird limit. Any conjectures about the value of this limit? Well, the top is going to infinity, and the bottom is going to infinity. I can't use a root test here. Remember, the root test is a convergence test for series. Here, I'm just trying to take a limit. If I had sigma n to the n over n plus 1 to the n, if I, instead of a limit here, I had a series sigma this thing, then a good test for that series would be the root test. But I don't have a series here, not at this point. I'm just trying to calculate the limit from the ratio test. So I'm already doing a convergence test. I need to stay within that and calculate this limit. Because the top and bottom are both going to infinity, your first thought might be L'Hopital's rule. But unfortunately, L'Hopital's rule isn't going to help us here. And the derivative of n to the n is actually quite scary. Requires something called logarithmic differentiation. And the same is true of the derivative of the bottom, quite scary. So we really don't want to use L'Hopital's rule here. I can make one suggestion. This is the same as n over n plus 1, all raised to the power n. And what we're going to end up doing here is we're going to lean on a sequence problem from 11.1 that was in your homework. So this I want to be clear first. This problem is hard, right? The limit here is hard. It's harder than something I would put on a test. It's good practice, and you need to understand this. Parts of this could show up on your test, but the whole thing here is quite tricky. So if I rewrite it like this is an indeterminate power. N over n plus 1 goes to 1, so this is 1 to the infinity, which is an indeterminate power. And the way you handle indeterminate powers is by taking the natural logarithm, manipulating it algebraically, and then applying L'Hopital's rule. You could do that. It would take another page and a half just to get through the calculation. So instead, like I said, we're going to lean on a previous problem. I'm going to rewrite this as lim n to infinity n plus 1 over n raised to the negative nth power. I take the reciprocal and the power becomes negative. And then I split this up as lim n to infinity n over n plus 1 over n is 1 plus 1 over n, all raised to the negative nth power. And at this stage, I need to ask if you remember the sequence problem from 11.1. This is a special limit. And while I wouldn't put this whole problem on a test, I could absolutely give you a problem like this. Yeah, thank you, Richard. This is your e to the ab limit. If you did the sequence homework, then you remember that 1 plus a over n, all raised to the bn, has limit e to the ab. This is a fact you absolutely want to remember for your test. Well, I can promise you that I wouldn't put this whole series problem on the test. I can also promise you that there will be at least one place on the test where you need to know this special limit. You can grind it out as an indeterminate power, taking logarithms and applying L'Hopital's rule, but it'll waste a lot of time. Got to remember this limit. This is an important limit. So this guy is this guy with a equal to 1 and b equal to negative 1. So this, by our special limit, is e to the 1 times negative 1, or e to the negative 1, or 1 over e by our special limit. So yeah, tricky series problem, but well within range of something you guys should be able to do on the homework. And the places where you need to recall something here, I'm trying to help you. Indeterminate powers, something that involves an indeterminate power could on its own show up on the test, just a sequence limit that requires you to work with indeterminate powers. These you, orange is done. For indeterminate powers, use Ln and L'Hopital's rule. That's how we handle those. So you would, instead of working with this directly, if you wanted to, you could take the natural log of this, which would be n times the natural log of n over n plus 1. Shove the n downstairs as a 1 over n. You get the natural log of n over n plus 1 divided by 1 over n. That now goes to 0 over 0, and you can apply L'Hopital's rule. Differentiating top and bottom, taking the limit again, you would get negative 1 out. So your answer would be that the natural log of your thing goes to negative 1, which means your thing goes to e to the negative 1. But it's about a page and a half of work to do this directly using natural logs and L'Hopital's rule. So instead, you want to try and, as soon as you realize this is a 1 to the infinity thing, you should try to shape it into this. I'll say that again. If you're taking a limit and you realize that that limit is in the form 1 to the infinity, you should try to reshape it into this so that you can use this special limit and just write down the answer. Okay, so the result here, I'm not done yet. Say it like this, since L equals 1 over E is smaller than 1, E is kind of close to 3. So 1 over E is kind of close to 1/3. A series S equals sigma n from 1 to infinity n factorial over n to the n converges absolutely by the ratio test. Now, of course, the convergence is absolute. The series has positive terms only, so convergence had to be absolute. But that's what the ratio test tells us. It tells us if L is less than 1, the series converges absolutely. So that's how we write it. Okay. I'm going to look at a problem from the study guide, the first one. We can do that. Before I do that, anything we want to look at more carefully here? Questions on what we did here, setting up the ratio test limit, simplifying the factorials, the algebra to get it into that special form. Okay. So we want to look at the first problem from the study guide, this guy. Integral 2 to infinity y e to the negative 6y dy. Hopefully you've already put some time into the study guide. Please work on it today. If you get that submitted to Canvas, then I can get in there and make some comments, which will help you on the test. So you really want to do that. Remember, to get credit for the study guide, you have to scan and upload your written work for the study guide problems. It's not about answering the questions in the assignment. All right, integral 2 to infinity y e to the negative 6y dy. This is a type 1 improper integral, right? Y and e to the negative 6y are both continuous everywhere. So there's no type 2 stuff. There's no vertical asymptotes here. We're integrating from 2 all the way up to infinity. So the infinity up here tells me it's a type 1 integral. And because this is continuous everywhere, we don't have to worry about any splitting up type 2 stuff. So the first thing we do, as with any improper integral, is rewrite it as a limit of proper integrals. So I'll rewrite lim r to infinity, integral 2 to r, y e to the negative 6y dy. And then it becomes about solving this regular old integral, right? We just kind of ignore the limit out front and crunch out the integral. Then we continue writing the limit because we want this to be equal to the original problem. But yeah, this is now a regular old definite integral. So how do you find an antiderivative for y e to the negative 6y? What kind of integral is this? Go back to your exam 1 stuff. By parts. Yeah, very good, by parts. You could try subbing for negative 6y, but that won't take care of this. You could change this into like e to the u, but then you'd have u over negative 6 out front. So if you have a polynomial, this is y here is a polynomial times an exponential, that's always integration by parts. Unless the polynomial is exactly the derivative of the power in the exponential. So I'll rewrite lim r to infinity, and then I'll open a big bracket. And what goes inside here is the stuff from my IBP. So we have to do some by parts. Little u is the polynomial piece. dv is the exponential, e to the negative 6y with the dy. du is just dy, and v is the integral of dv is negative 1/6 e to the negative 6y. So what goes in my big bracket over here is u times v. I'll write the constant out front. This is negative 1/6, and then y e to the negative 6y. Evaluated between bounds, evaluated from 2 to r, minus the integral from 2 to r of v times du, which is negative 6 e to the negative 6y dy. So negative 1/6 e to the negative 6y dy. People make mistakes here by forgetting to evaluate the first chunk, right? When you do integration by parts on a definite integral, every piece gets evaluated between bounds. So don't forget the evaluation here. Remember to keep writing your limit up front. Our goal is now to calculate this integral and then evaluate everything and then take the limit. So my AP stuff, I have now lim r to infinity. When I plug in the r here, well, maybe I'll save the evaluation for now. Save some space. I'll evaluate to r. And then the 1/6 is going to pop out. The negative will make this positive. Integral 2 to r. Oh, shit. 1/6 integral 2 to r e to the negative 6y dy. And I'll continue over here where I have some space. Still writing lim r to infinity. And then big bracket. All right. This piece, normally I would say go ahead and evaluate this, but there's no harm in leaving it for now. We'll get there. When I integrate e to the negative 6y, I'll get negative 1/6 e to the negative 6y. So this is going to become a minus 1 over 36 from the extra copy of negative 1/6, and then e to the negative 6y evaluated from 2 to r. And this piece is also evaluated from 2 to r. Okay. So I need to plug 2 into everything and then subtract what I get when I plug r into everything. Let's go ahead and do that, and then we'll try to figure out our limit. When I plug r in, upper minus lower, of course, when I plug r in here, I'll get negative 1/6 r e to the negative 6r. And from that, I'm going to subtract what I get when I plug in 2. So the minus that you get from the evaluation is going to make this positive. So I'll have plus 1/6 times 2 e to the negative 6 times 2. That is, everything in the line below is just this piece. So I plugged in my upper bound r, that's this. And then I subtract what I get when I plug in my lower bound 2. And when you subtract this piece, that minus and this minus make this a plus. Then I have minus 1 over 36 e to the negative 6r. And again, when I evaluate this at the lower bound, I'm going to subtract what I get when I plug in 2. Minus minus makes plus. So this is plus 1 over 36 e to the negative 6 times 2. There she is. So this term and this term are like terms. They're both e to the negative 12 stuff. I've got here 2/6, which is 1/3 e to the negative 12, plus 1/36 e to the negative 12. So let me just group those out front. Those are, of course, constants. I'm not terribly worried about them. The other two pieces, negative 1/36 e to the negative 6r. And minus 1/6 r e to the negative 6r. These we have to think about a little bit. Let's tackle this guy first. what does e to the negative 6r do as r goes to infinity? So r is going to infinity. So this is like e to the negative 6 times infinity. Okay, yeah, a bunch of different conjectures here in chat. Exponentials are always positive, right? E to some stuff will never be negative anything. So the graph y equals e to the negative 6r. Looks like this. It's a decaying exponential, right? Like e to the negative x. So this piece goes to 0. Which also means that this piece wants to go to 0, but the r here wants to go to infinity. So here I've got negative 136 times 0. When you take the limit, he's gone. Here I've got negative 1/6 times infinity times 0. That second piece is, that fourth piece, this last piece over here is a problem. Now 1/3 plus 1 over 36. Let's see, 12 times 3 is 36, right? So this is 1236 plus 136 is 1336. e to the negative 12. That's that first piece, or the first two pieces put together. This middle piece here is 0, and this last piece here requires some love. So we said the e to the negative 6r here, this guy wants to go to 0. The r here wants to go to infinity. So this is like infinity times 0. What is infinity times 0? Could be 0, could be infinity, and it could be anything in between. Infinity times 0 is an indeterminate form, yeah. So r e to the negative 6r goes to infinity times 0, which is an indeterminate, it's a specific kind of indeterminate form. It's an indeterminate product. And the way you handle indeterminate products is by turning them into indeterminate ratios and applying L'Hopital's rule. So this is lim r to infinity, 1336 e to the negative 12 minus 1/6. So if you have something that looks like infinity times 0, you need to rewrite it as a fraction. I can rewrite this as r over e to the 6r. And then by applying L'Hopital's rule once, now r over e to the 6r goes to infinity over infinity, which is an indeterminate ratio. So I can apply L'Hopital's rule. This constant piece here, I'm not doing anything with him anymore. He's done. I'm just working with this. The derivative of r is 1. The derivative of e to the 6r is 6 e to the 6r. And now 1 over 6 e to the 6r goes to 1 over 6 times infinity, which is 0. So this piece right here goes to 0. And by L'Hopital's rule, that's the same as this piece, which was the thing we were working with. So what do we get? I get 13 over 36 e to the negative 12. It's this guy. It's 0 by L'Hopital's rule. All right, that whole fraction. So the integral converges. Integral 2 to infinity y e to the negative 6y dy converges to the positive number 1336 e to the negative 12. And that is your answer. All right, so this one does involve a bit of work. You got to do some integration by parts. Then when you go to calculate your limit at the end, one of the pieces is nice. The other piece requires some L'Hopital's rule, not super easy. Questions on what we did here? Okay. What else do you guys want to see? So we're only about halfway through the class. We can do whatever else you guys would like to do. Yeah, of course.
I was going through the lectures and I saw on one of the things that you said, it's a fact that n equals 1, like the series of n equals 1 to infinity, of 1 over n will always diverge because it's a harmonic series. Are we able to use that on the test and say it's a harmonic series and it diverges?
Yeah. Yep. Or you can just say it's a p-series, right? 1 over n is a p-series with p equal to 1. So that's a special case of the result on p-series. But if you want to say because the harmonic series is known to diverge, instead of saying because it's a p-series with p equals 1, that's fine.
Okay. Thank you.
Yeah, yeah, of course. While we're talking about the harmonic series, it's easy to get the impression that divergent series are boring. But there is a neat fact. This thing, the difference between the harmonic series partial sum and the partial integral for the 1 over x, both of which are divergent if you let r be infinity. But if you subtract them and send r to infinity, if you take the limit as r goes to infinity of this, so like this divergent series minus this divergent integral, this is a number called gamma. It's called the Euler-Mascheroni constant. Don't fret, I promise you I'm not going to put anything about this on the test, but it is a cool thing. And I have a funny story about this. A friend of mine was getting into a taxi cab here in Gainesville, going to the airport, about to fly out to a math conference. And the cabbie asked him, what do you do? He's a mathematician. Where are you going? I'm going to math conference. The cabbie turns around and says, say, is it known yet whether the Euler-Mascheroni constant is rational or irrational? And it's just interesting. Gainesville's a funny town like that. The joke is that analytic number theorists end up driving taxi cabs because there are no jobs for us. But it's an important constant in number theory, and it's not known whether it is rational or irrational yet. Okay, so we do have another question in chat now. Can we explain when to use the direct comparison test versus the limit comparison test? Generally, the direct comparison test is faster because the direct comparison test gives you a result pretty quickly, right? If you say my series is smaller than this convergent series, then your series is convergent. If you say my series is larger than this divergent series, then my series is divergent. The limit comparison test is useful when you can't make that smaller, larger statement. So direct comparison is quicker when you can see the inequality. But if you can't find an inequality to use the direct comparison test, then the limit comparison test is the way to go. Classic examples here. So direct comparison test versus limit comparison test. If I have the series S equals sigma n from 1 to infinity 1 over n squared plus 2, and t is sigma n from 1 to infinity 1 over n squared minus 2. Actually, let me start the series here at 2. Terms to be positive. One of these is a good candidate for direct comparison. One of them is a good candidate for limit comparison. First, do these series converge or diverge? What's your gut feeling and why? Yeah, they both converge. They both converge because they're both very similar to 1 over n squared. 1 over n squared, right? Super duper similar. The two, whether you're adding it or subtracting it, really doesn't have any impact on the convergence. So both converge. Which series is better suited to direct comparison? Which series is easy to squeeze underneath a convergent series? Yeah, Richard's got it in the chat there. So 1 over n squared plus 2 is smaller than 1 over n squared. So this guy, series S, is easy to use a direct comparison. Why is this inequality true? Because his denominator is bigger. Bigger denominator makes you smaller overall. And the terms are positive. So since sigma 1 over n squared is a convergent p-series, it follows from the inequality, which I'll call star, that S converges also. P-series here, P is equal to 2, which is bigger than 1. So neither of my original series are P-series, right? The other stuff going on in the denominator ruins the P-ness of the series. It's not a P-series because it's not just 1 over n to some power. But the series S, I can easily compare those terms to the 1 over n squared series. N squared plus 2 is bigger than n squared. So 1 over n squared plus 2 is smaller than 1 over n squared. And that means that since this series has terms which are smaller than the sigma 1 over n squared p series, it follows from this inequality that the series S must converge. On the other hand, t here, t's got a problem. See, 1 over n squared minus 2 is not smaller than 1 over n squared. His denominator is smaller than 1 over n squared, which makes him larger overall. So for the series, the obvious inequality is 1 over n squared minus 2 is bigger than 1 over n squared. which isn't useful in DCT. Right? Being bigger than a convergent series doesn't tell you anything. So LCT is the way to go, limit comparison. And if I run the limit comparison here, I pick Bn to be 1 over n squared. I still want to compare to that. That's the series that these are both super similar to. And I compute L as the limit n goes to infinity. No absolute values here, sorry, bad habit. N over Bn, which is when n to infinity, 1 over n squared minus 2 divided by 1 over n squared, which is limit n to infinity, n squared over n squared minus 2. And either by one application of L'Hopital's rule or by renormalization, or just because you've seen it a million times, this limit is 1. And then to finish things up, you have to say, since this limit is 1, which is positive and finite, my series T and the series sigma 1 over n squared converge or diverge together. And then you still have to say, moreover, sigma 1 over n squared is a convergent p-series. Why? Because p is 2, which is bigger than 1. So T also converges. All right, so both of these series converge. But you cannot prove that T converges using direct comparison because the sort of natural inequality points the wrong way. My series is not smaller than the related p-series, it's larger than the related p-series. But it's just a little bit larger. Still, without the right inequality, you can't use direct comparison. So we use limit comparison instead. So anytime you can like tell that your series is very similar to a nice series, geometric or p-series, but you cannot get the inequality you want, you should use limit comparison. If you can get the inequality you want, you should use direct comparison because it's more direct, right? Just compare the amount of work. Here, this is like 1, 2 lines. Here, this is more, right? Now, even if you just jump to the solution here, it's more. So limit comparison is more powerful, but it takes a little bit more effort on your part. Our theorem on growth rates. I got a DM asking to review the theorem on growth rates. It's this. Says that any power of the natural log is completely dominated by a regular power, is completely dominated by any growing exponential, is completely dominated by the factorial, which is completely dominated by the super exponential, where P, Q are positive, and B is bigger than 1, and AN less than BN means lim n to infinity, AN over BN equals 0. So this is, it's just a handy fact to know that any power of the logarithm is dominated by any power function. is dominated by any growing exponential, is dominated by any factorial, is dominated by the n to the n super exponential. There's a few places where I had opportunity to use this, like one of your homework problems involved the sum n over the natural log of n all to the p, and we asked for what values of p does that converge, something like that. This fact is useful in showing that it was an alternating series, right? It was the alternating n divided by natural log of n all to the p, and showing that that limit is zero, that the limit of the bn's is zero there can be done immediately through this growth rate thing. Okay, what else, guys? What else? Like, for example, if you needed to calculate the limit as n goes to infinity of say the natural log of n to the 2021 divided by n cubed, this is equal to 0 by growth rates. Or where else did we use this? The limit as n goes to infinity of n factorial over n to the n equals 0 by growth rates.
Will there be growth rates problem on the test?
I'm not going to ask you anything explicitly about this. You can use it, right? That's all it's here for. So you can, if you're looking at a limit and you don't want to take the time to calculate the limit, like this n factorial over n to the n limit, which is kind of a pain in the ass, you can just say, oh, it's 0 by growth rates. But I'm not going to like give you a problem couched in terms of this notation. Yeah, let's look at canceling some factorials. And some not quite factorial things. Well, actually, here, hang on. Let an be this. And let's simplify the ratio test limit, ratio test object here. And this is similar to something we did the other day. It might be identical to something we did the other day. The trick is that an plus 1 would be 2 times 4 times 6. You just replace the n by n plus 1. So the last term here would be 2 times parentheses n plus 1. And what's the pattern upstairs? It's the product of the first n even numbers. So the term that would come right before this would just be 2n. And I think it's nice to write the last few terms and the first few terms. Downstairs, n factorial itself, remember what the factorial is. By definition, n factorial is the product of all the positive integers less than or equal to n. So this would be n times n minus 1 times n minus 2, all the way down to 3 times 2 times 1. So an plus 1 divided by an would be 2 times 4 times 6 out to 2n times, this would be 2n plus 2 divided by n times n minus 1 times n minus 2. Oh, sorry, this n plus 1 factorial. So sorry. Down to 3 times 2 times 1. And then if I divide by an, that is n factorial, n times n minus 1 times n minus 2 down to 3 times 2 times 1, divided by the original numerator, which is 2 times 4 times 6 out to 2n. So there's a boatload of cancellation that could be done here. And you get 2n plus 2 over n plus 1. So this is something that could show up in a ratio test. If we had sigma this thing, then the object you would take the limit of for the ratio test would be this, which is this. Let me look at one other kind of weird factorial-ish object, just to see how we're feeling. I put one of these somewhere in your study guide. Maybe not. Yeah, something like this. Let me actually, where's your textbook? Something a little weirder. Let's see, so. Yeah, I guess the answer to your question is yes. So the question was kind of, I'll come back here real quick. Is this relation transitive? And yes, the answer is. So it is true, for example, that n to the q is less than n factorial. So if you were to look at n factorial, n to the q divided by n factorial, that would go to 0. Or the natural log of n all to the p divided by b to the n, that would go to 0. So if I am less than you, and you are less than Sheila, then I am less than Sheila. Test 2's average, last time I taught this class was over the summer, it was around 65. But test 1's average was around 70 over the summer. So it's, it's hard to say. The tests were quite similar. Us having that very, very low average on the first test is extremely weird. That's not something I've ever seen before. Okay. So did we get to work out 24 last time? I think we worked out this one and this one, but maybe not 24. Let's take a look at 24 here. So sigma (1 to infinity, negative 1 to the n, 2 to the n times n factorial divided by this weird factorial-like product, 5 times 8 times 11, all the way up to 3n plus 2. All right. I think the trick to this series and the trick to managing all of these sort of products, the type Kylie was asking about, is to understand what the hell this denominator is even communicating. So to get started here, I'm going to write out the first few terms of the series. When n is 1, this is negative 1 to the 1. This is 2 to the 1. This is 1 factorial. So this is negative 2 divided by this product when n is equal to 1. If you plug 1 in here, this is 3 times 1 plus 2 is 5. So this is supposed to be 5 times 8 times 11 all the way up to 5, which means it's just 5. The next term would be negative 1 squared, which is positive, times 2 to the 2, which is 4, times 2 factorial, divided by 5 times 8. The next term would be minus 2 to the 3, which is 8 times 3 factorial, divided by 5 times 8 times 11. The next term would be 2 to the 4, which is 16 times 2 factorial, And let's figure out the denominator here. This is the first one we have to think a little bit on. Be 5 times 8 times 11 times whatever the next thing is in that pattern. And you can plug in n equals 4 here. You get 3 times 4 is 12 plus 2 is 14. So this would be 5 times 8 times 11 times 14. I plugged in n equals 1 here. So where did the 2/5 come from? That's negative 1 to the 1, which is negative 2 to the 1 times 1 factorial. Maybe I should write 1 factorial. And then the downstairs product here, when you plug in 1 for n, this is the way people would normally read this is the product of all the numbers of the form 3n plus 2. So when you look at this denominator, when n is equal to 1, you see that the last term in this product is 5, right? 3 times 1 plus 2 is 5. So this is supposed to be 5 times 5 plus 3 times that plus 3, all the way up to 3n plus 2. Well, if 3n plus 2 is 5, then the only term in this product is 5. So I'm just trying to explain how to interpret these sorts of products. So when n is 1, the downstairs has 1 term. When n is 2, the downstairs has 2 terms. When n is 3, the downstairs has 3 terms. When n is 4, the downstairs has 4 terms. And they always follow this pattern of start with 5 and then add 2. Start with 5 and then add 3, add 3, add 3, add 3.
Can I ask, like, how do you know you have to add like 3 to get to the 3n plus 2?
Well, what is 3n plus 2? It's a linear function where you add 3 every time you go over 1, right? It's like you can think of this as like a linear function with slope 3. There's a handful of ways to do it, but I'll also just look here, right? The first few terms are 5, 8, 11. What's the pattern? We're going up by 3 each time. Let's try a couple more like this. So let me say, we haven't investigated the series at all yet, but I think the goal is to mess with the products. Yeah, let's go ahead and test the series. So we're just writing out the first few terms there. The test here would be the ratio test. And this will give us some practice writing out factorials. The last term I wrote out is 16 times 2 to the 4. 16 is 2 to the 4. 16 times 4 factorial. Sorry. So it's 2 to the n times n factorial. It's the numerator. 16 times 4 factorial divided by 5 times 8 times 11 times 14.
How did you decide to use the ratio test?
Factorials. So there's an n factorial upstairs, and there's a factorial-like product downstairs. If you wanted to write this in multifactorial notation, the denominator would be 3n plus 2 triple factorial. But both this thing and this thing hint strongly at the ratio test. All right. So we know we need L as the limit n goes to infinity, absolute value an plus 1 over an. Remember on the test, if you at least write this after the ratio test, even if you mess everything else up, I can give you a point or two for remembering what the ratio test says. So always wise. I'm going to write out an plus 1 and then multiply by the reciprocal of an. So an plus 1 is negative 1 to the n plus 1 times 2 to the n plus 1 times n plus 1 factorial, and we will eventually write out that n plus 1 factorial. The tricky part, though, is the product downstairs. So if 5 times 8 times 11 out to 3n plus 2 is the denominator of an, let me just write that over here. Here's the denominator of an, 5 times 8 times 11 up to 3n plus 2. I'll write out the other easy parts here, which are 2 to the n factorial and negative 1 to the n. What is the denominator of an plus 1? What is this product taken to have one more term?
(3n plus 5).
Yeah, very good. This would be 5 times 8 times 11. And I would just write it as here 3n plus 2, and then 3 times n plus 1 plus 2. Right? So the product in the bottom has one more term every time n goes up by 1. So the product in the bottom of an plus 1 is the same as the product in the bottom of an, just with one more term following that same pattern. And you're correct that this is 3n plus 5. So if I continue over here, I have lim n to infinity, absolute value of, I'll group all the like stuff together, -1 to the n plus 1 over -1 to the n, 2 to the n plus 1 over 2 to the n plus 1 factorial over n factorial. And then my weird product, 5, 8, 11 out to 3n plus 2 divided by 5, 8, 11, 3n plus 2, and then 3 times n plus 1 is 3n plus 3, plus 2 is 3n plus 5. So here's my ratio test limit written out in a nice form where I can start working with things. -1 to the n plus 1 divided by -1 to the n is -1. 2 to the n plus 1 divided by 2 to the n is 2. N plus 1 factorial divided by n factorial is just n plus 1. Maybe I'll write that out for you. So this is lim n to infinity, absolute value of -1 times 2 times n plus 1 factorial. The factorial of anything is that thing times that thing minus 1 times that thing minus 2 times that thing minus 3, all the way down to 3 times 2 times 1. So you just start at whatever is inside the factorial, and then you multiply that thing by all the positive things less than that. N factorial is n times n minus 1 times n minus 2, all the way down to 3 times 2 times 1. And then in this weird product, I can cancel the stuff out to 3n plus 2. I'm just left with 1 over 3n plus 5. The absolute value is just going to get rid of the -1 factor here. The 2 can come out. I'll just write it like this. This is lim n to infinity 2 times. Here, the n factorial downstairs will cancel with the copy of n factorial hiding within n plus 1 factorial. So I've got n plus 1 over 3n plus 5. And n plus 1 over 3n plus 5 goes to 1/3. So the whole limit here is 2/3, which is less than 1. So S converges absolutely. By the ratio test.
Wait, could you explain that 2/3 less than 1 again, please?
Well, I'm just saying, so L is equal to 2/3, my limit, which came out to this thing. The 2 comes along for the ride, and n plus 1 over 3n plus 5 goes to 1/3. So that's 2/3 for the limit. And 2/3 is smaller than 1. So I'm just making a statement. If you
Wait,
want,
how did it go to 2/3 if infinity over infinity is an indeterminate ratio?
well, remember, we've got a bunch of different ways we can calculate these limits. We need to be practiced with this. So if you want to look at lim n to infinity, n plus 1 over 3n plus 5, you've got two choices. It is infinity over infinity, which is an indeterminate form. So there's two ways you can handle that. You can either use L'Hopital's rule, or you can use our renormalization trick where you divide top and bottom by the fastest growing term. So if I divide top and bottom by n, I get 1 plus 1 over n divided by 3 plus 5 over n. And 1 over n and 5 over n both go to 0. So this is 1 plus 0 divided by 3 plus 0, which is 1/3. And then 2 times 1/3. That's our 2/3. And we could, if we want to, say because L equals 2/3, which is less than 1, if you want to split those claims up.
What happened? Like, if I forget to write absolutely, would I get points off on the test?
A little bit. Yep, a little bit.
So do we have to like write the absolutely for every investigate question?
I will very clearly state in the problem whether I need you to tell me whether the series just converges or diverges, or whether I need you to tell me that the series converges absolutely, conditionally, or diverges. But the important thing here is that you remember what the tests each say. And the ratio test, when L is less than 1, always tells you that the series converges absolutely. So if you're using the root test or the ratio test, just remember that the positive result there is absolute convergence. No, I'm not going to make you probe absolute versus conditional convergence for every series, but if the test you're using has as its output, this series converges absolutely, then you do need to tell me that. So I got a couple questions that came in DMs, and then I'll get to your question there, Richard. Where did the 3n plus 2 and 3n plus 5 come from? That's the big question, right? How did we get this denominator? This is the part that we need to think carefully about. The answer is looking at the denominator of the original terms here. What would be the next term in this product? So the pattern here is that you start at 5, and then you multiply all of the numbers. You take the product of 5 with 5 plus 3, with that plus 3, with that plus 3. So the pattern in this denominator is that you've got a product like 5 times 8, 5 times 11, 5 times 11 times 14. The next one here would be 5 times 11 times 14 times 17. In other words, if you're going to extend this product by one term, if you're going to look at the next term in this product, that would be 3n, 3 times n plus 1 plus 2, right? And then distributing the 3 here, 3 times n plus 1 is 3n plus 3. 3n plus 3 plus 2 is 3n plus 5. I do want to look at one more thing like that where we're just playing around with a product, not in the context of a ratio test. And then I'll talk about absolute versus conditional convergence. All right. So if an is, let's say, 1 times 5 times 9 times 13 all the way out to 4n plus 1. What is a sub n plus 1? So let me just write out A1, A2, A3. So A0 here would be 1. A1 here is 1 times 5. A2 here is 1 times 5 times 9. A3 would be 1 times 5 times 9 times 13. A4 would be 1 times 5 times 9 times 13 times 17. And I'll even write A5 would be 1 times 5 times 9 times 13 times 17 times 21. Right, you see the pattern? When n goes up by 1, there's one more term in the product. And the next term is always 4 larger than the previous term. So a sub n plus 1 would be 1 times 5 times 9 times 13 up to 4n plus 1, which is so far just an. And then the next term in the product would be 4 times n plus 1, which is 1 times 5 times 9 times 13, all the way out to 4n plus 1. And this 4n plus 4 plus 1 is 4n plus 5, which is 4 larger than the previous term. All right. That's enough on these weird factorial-like products. They will show up, and they will show up when we talk about power series a little bit later. But it's definitely not the main point of the test, right? The main point of the test is convergence questions. So absolute versus conditional convergence. Oh, and then we got to go. Okay. Remember the definition. If sigma absolute value of an converges, then that means sigma an converges absolutely. That's the definition of absolute convergence, right? Your series converges absolutely if the new series you get by swapping an for its absolute value is itself convergent. And then if your series converges but does not converge absolutely, if sigma an converges, but sigma absolute value an diverges, then the original series, sigma an, converges conditionally. We don't have a test that will tell you this series converges conditionally, right? There is no test that has that as its output. But what Prashant said about alternating series has a hint of truth to it. Namely, most of the conditionally convergent series we will see, in fact, all of the conditionally convergent series we will see are alternating series. If a series has exclusively positive terms, then if it converges, it must converge absolutely because the absolute value series is the same as the original series. But some alternating series converge, but then when you take away the -1 to the n, diverge. In other words, if you have an alternating series that diverges when you get rid of the alternatingness, then what you're looking at is a conditionally convergent series. So the place you're going to see this specifically, if sigma -1 to the n bn converges, but sigma bn on its own diverges, then that original series, sigma -1 to the n bn, converges conditionally. That's the idea. If you have an alternating series that would diverge if it didn't alternate, that is a conditionally convergent series. I'm not quite sure the question there, Jose. So if we ignore the first numbers or constants of the sequence, what do you mean exactly?
Just like the 1 times 5 times the first numbers.
What do you mean by ignore?
Like not writing it in the equation in the work.
Not necessarily. So like if you're doing a ratio test that involves something like this, then you don't need to write this, but you do need to write, like if you just wrote 4n plus 1 instead of 1 times 5 times 9 times 13 times 4n plus 1, then that would be incorrect, right? This is much, much larger than 4n plus 1. This is a product with n terms in it, the last one of which is 4n plus 1. So yeah, a quick, I guess, comment here. This is not the same as 4n plus 1 itself. I think that's what you mean, right?
Yep.
Yeah, so if we were working with this thing or something that contained this in a ratio test, and instead of writing the whole thing, you just wrote 4n plus 1, that would be incorrect. Not only would it be incorrect notation, but it would probably butcher the answer. It would probably yield the wrong answer. That's like saying n is the same as n factorial. And n factorial is, of course, much, much larger. All right, I got another class that starts in 3 minutes, so I got to dip, guys. I wish you all the best of luck. I do have an office hour this afternoon from 1 to 2. If you've got some questions that are driving you nuts, please work hard over these next 2 days. Study hard. Make sure you know your theorems. Make sure you know your tests. Make sure you know their hypotheses and their conclusions. And then when it comes to the test day, come in calm. Take a little bit of time, eat a good breakfast, meditate, do whatever you got to do to get your brain at ease, and think as clearly and carefully as you can on the day of the test, and it will be okay. That's it. I'll see you guys later.